So now we have done a bunch of calculations, small signal calculations on this 5 transistor OTA, and we also know what is the gain of this. So let us say you design this, and let's say you design this for a very, very large gain. And why do you want to make amplifiers with infinitely large gain? To be used in negative feedback. So let us say you design such an amplifier, let's say this 5 transistor op amp itself, and you use it to form an inverting amplifier like this, for example. So again, if I call this R1, R2, so if the small signal voltage is some Vi, what will be the output here? Inverting amplifier. Great. Minus R2 by R1 times Vi. And of course, I mean, now we will not use an op amp, we have an OTA. So, but again, as long as the gain is really large, the output is still the same. Now by this time it should be clear that I can't actually connect this to ground 0 volt, right, because this is going to the gate of a transistor. So this is just a small signal ground. So in practice, where will I connect this to? Some DC voltage source. I'll call it some bias voltage VB. Similarly, the small signal voltage should also not be given directly. I'll use some other bias voltage. I'll use the same voltage for simplicity. Okay. So which means even at the output side, I will have some bias voltage plus the small signal part. Correct? Let's try to find what is this DC output, I mean DC voltage at the output. So let's argue this way. Let us say the op amp you have designed has an infinitely large gain. So then what can you say about this potential approximately? That is also VB. Infinitely large gain. You put in negative feedback, you can use the virtual ground principle. So which means let's look at only the DC signals, so only the LO signals. What is the DC current flowing through R1? 0 amps. So then what is the DC current flowing through R2? If the DC current flowing is 0 and the DC voltage here is VB, what should the DC voltage here be? You can write it directly. Is it clear? So now let's say you have designed this op amp and you are trying to sell it. Now if a customer asks that, hey, can I use any value of Vi here and my op amp, will my op amp work? What will be your question? What will be your response? I mean, yeah, how small, or like how will you decide? What decides that? Forget about the small signal case. Is there something? Yeah, small signal is correct, but let us say I ask for both V bias and Vi. Can I use any random voltage for VB? Why? Why not? You want to keep it in saturation. Similarly, I can't have an arbitrary large Vi. Firstly, small signal thing is there. Secondly, I mean, if let us say I use large Vi, so this becomes really small. A positive voltage, negative voltage, this voltage will go really low. Things will go out of saturation. Right? So we need to specify what is the range of voltages I can apply here, so that the transistors are all in saturation. That is your important concern. Correct? One is definitely small signal, but at least it should make sure that the transistors are in saturation. So that is an even bigger concern, right? So, but in practice, it is not practical to specify, hey, in this circuit, use this values of VV and this values of Vi. That doesn't work out because you never know what is the gain here. Let's say some customer uses it to make a gain of 2. Some guy wants to make a gain of 100. Then the values you specify will be different for different circuit. And there might be some guy who wants to use it in a non-inverting configuration like this also. Then here the calculations will be different. So the point I'm getting at is, it is not practical to specify for a particular circuit use this values of VB, this values of VA, because you never know what is the end application of the op amp. All you know is the customer will use it in negative feedback, but what kind of circuit in negative feedback is not under your control. So instead of specifying the ranges on the bias and the input directly, what is done is the following. We specify the maximum and minimum you can apply at the input and the output. You specify, hey, my op amp can take a range of voltages for my non-inverting terminal, a range of voltages for my inverting terminal, and this range of voltages at the output. Only then all the transistors will be in saturation. The moment you specify these ranges, now depending on your circuit, you can easily calculate. For example, in this circuit, you see the inverting terminal is equal to VB. If you know the limit on V plus, you know what is the limits for VB. So similarly, I know what is my V out, so I can find out what is the limit on VA. Okay. Is it part clear? So instead of actually specifying the ranges for bias voltage and the input, what is specified is the limits on the inputs of the op amp and the output of the op amp. Okay. And even here, if you make this following observation, because I know this is going to be used in negative feedback, what can I say about the inverting and non-inverting terminals? They are going to be approximately equal. They will be same, right? So which means instead of considering the two voltages independently or individually, we can consider them as a differential mode part. I will say it is basically V plus minus V minus, and a common mode part which is V plus. And what is the differential part here? That's approximately 0. I don't have to worry about the differential part because it's going to be 0. I'll only worry about the common mode part. So this is, we'll denote this as VICM, or we'll say this is the input common mode range, or I'll say input common mode, sorry. Okay. The logic is simple. I mean, you see that both inverting and non-inverting terminals are at the same potential. So there is no need to specify limits for both of them individually. I'll just say what is the common voltage I can have on both V plus and V minus. That's all. So in practice, we specify only the limits on this, the input common mode and my output. So let us say for your op amp, this is specified. Then the customer will know what kind of circuit the op amp is going to be used in. Let us say, for example, it is used in this kind of a circuit. In this particular example, what is my VICM? What is the input common mode for this circuit? Sorry? No. I mean, when I say VICM, it is the common mode at the input of the op amp. How much is that? VB. So which means if I know the range of voltages I can have for the input common mode, it is very trivial to know what is the range I can have for VB. Similarly for Vout, here what is the Vout in this particular example? This VB minus the gain, let us say, I'll say some gain times VA. So I already know what is the range I can have for VB. I know what is the gain I'm going to use. So if I know what is the range of voltages I can have for Vout, even the input I can apply, you know. Okay. So similarly, if I use it in this circuit, VICM will be different. So for example, here if I do it, I'll apply VB plus VI, correct? So maybe I'll take this, yeah. If I use it in this configuration, this is VB plus VI. So what will the output be here? Approximately? Huh? I mean, what will the output be? VB plus VI. Again, the op amp, let's assume that it has an infinitely large gain. So these two potentials will be same. So in this particular circuit, what is VICM? let me actually show it here. Yeah. So in the circuit, what is VICM? VB plus VI. And what is my Vout? VB plus VI, right? So which means you kind of know what is the range of voltages I can have for this. What is the range of voltages I can have for this? So I know what is the VB plus VI I can have. So for example, let us say for VICM, let us say the limit is, for example, 0.2 volt to 0.8 volts. This is, let us say, for the VICM. Similarly, my op amp's Vout maximum is, let us say, 1 volt, minimum is 0.3 volt. So what will be the range of voltage I can have for VB plus VI now? What is the lowest I can go now? I mean, VICM, the limit is 0.2. For Vout, it is 0.3. In my particular circuit, both VICM and Vout are equal. So which means I have the same VB plus VI on both. So what is the lowest I can take? 0.2 or 0.3? Yeah, 0.3. Similarly, max is how much? So now you know the range for VB plus VI. So you say, I'll use some particular value of VB. Then I'll know what is the maximum minimum for VI. So that's what we'll do in the next class. So we'll try to compute what is this input common mode range. I mean, range of voltages I can have for the input common mode, and the range of voltages I can have for my output. So we'll stop here and we'll resume. Yes?
So in previous cases, we are finding the value of VI by checking the linearity of circuit.
Correct.
So here, like if we have the Vout and VICM range, and we calculate some VI values, so will it happen that it will go out from the ranges of linearity?
Yeah, definitely. But the point is, see, you have small signal. For a transistor, what is a VI? I mean, for a transistor, I know VGS must be less than 2 times VGS minus VTH. Correct? This is for my small signal approximation to be valid, right? But at least we want to make sure that the transistor is in saturation, right? So this is a much stricter limit, but you don't want to give very strict limits on the end application. As long as your transistor is in saturation, it is going to reasonably work, right? Because finally I want to bias my transistor in, this is VDS and ID. I want to bias it in this range, that's all. Now around a given operating point, for small signals, maybe I have to swing only so much, correct? But the operating point itself can take any values here, correct? We are specifying that limit. I'll elaborate in the next class if it's not clear. So we'll continue from this point in the next class. Yeah.